My name is Max Townshend of Townshend Audio, the company which I founded in 1975. Our goal has always been to apply engineering solutions to the often described black art of high-end audio. Our rigorous engineering approach has led us to conclude that there is only one correct solution to many of the contentious aspects of accurate audio reproduction. We have produced a number of short videos to demonstrate our unique solutions to some key aspects of our designs. This is an experiment to show that loudspeaker cables affect the sound. And what we're going to do is we're going to use the simplest possible test equipment, namely a very basic audio oscillator set at 2 kHz with a square wave, feeding into a Cambridge audio amplifier, a very basic integrated amplifier, which is then connected by a speaker cable to a two-way loudspeaker here. The driver's around the other side on the front. Then we have a regular 2-beam oscilloscope connected. One beam, the top beam, is connected to the output of the amplifier, and the bottom beam here is connected to the speaker. So we're looking at each end of the speaker cable. Now in this instance here we're using a regular piece of figure-of-8 cable, which you can see here. It's just a very basic cable which we're connecting from here to here, and then we're going to turn on the audio oscillator here, and you can hear the tone from the square wave, and you can see the 2 beams here. Now if you look carefully you can see that the bottom beam is slightly distorted here compared with the signal out of the amplifier, and if I press this button here, we've now inverted this bottom beam, and the function subtracts this beam from that beam. So what we get is the difference between the two signals, the difference between the signal on the amplifier and the speaker. And you can see there you've got the little glitches. Now what we're going to do is to substitute Townshend Audio speaker cable for the regular figure-of-8. And here we have it being positioned there. And now you can see the output signal from the amplifier and the signal on the speaker inverted, and the difference. And if you notice this time it's virtually a dead straight line, which shows that the difference between this cable input and output is far less of a difference than with this cable. And the reason for it is not the fact that it's thicker wire, it's due to the geometry. And to show that, we have here, and I'm going to unplug that now, we have 2 pieces of identical copper strip as is in the cable, and I'm going to connect this one to the red there. That signal is being transmitted through the oscilloscope probe, so I'll put this one on here to short out that one, and you can see now we have the same little glitches there, which shows that it's the geometry of the cable, not the DC resistance of the cable, which causes these little anomalies. And those little spikes there cause distortion to the signal. So when we now remove this cable, and I'll substitute back the Townshend cable, you will see once again we've got identical signal input and output with no difference, because this is a straight line. And the beauty of that is that you can have a much longer lead without any distortion, and we could also have unequal lengths. So you can have 2 meters one side and 5 meters or 10 meters the other side, and there's no difference in the sound. In this instance we're going to do a different form of cable, which is our earlier Isolda cable, which comprises 6 slots of 50 ohm coax paralleled together. So 50 divided by 6 is 8.2 ohms, and we do the same setup as before, connecting it, and once again you can see that there's no difference between the input and output. It's virtually a straight line there. And I will now substitute another highly regarded cable. In this instance, it's a purple one, and if we plug that in there, you can see here there's a really large difference between the input and the output. And you can see this step here, that up down, that's due to the high DC resistance of this cable, and you can see the severe spike that's at the transient. And this is a cable with a characteristic impedance of about 150 ohms, but a relatively high DC resistance. And we're now going to substitute here with some very common sort of speaker cable here, which comprises two very heavy conductors together with very low resistance. And plug that in here. You can see it's quite good. There's no DC step, but there's still the little spike due to the spacing of the cable. And once again, when we go back to the Isolda cable, which is this one over here, you can connect that to there and that to there. You can see that there is no difference between the input and the output. And this cable, and the reason for that is it's got high capacitance and very low inductance, so that the square root of the inductance divided by the capacitance works out to be about 8 ohms. And this proves that transmission line properties occur at audio frequencies, very often denied by people who don't really understand the difference between a long transmission line and a short transmission line. And if you look at our website www.townshendaudio.com, there's a more complete explanation of what's going on.